In quantum computing, we use quantum bits, or qubits, as the basic unit of information. Unlike classical bits, which can only take on the values of 0 or 1, qubits can exist in a superposition of both states at the same time. This allows for a massive increase in computational power when dealing with complex problems. One of the key mathematical operations in quantum computing is the tensor product. The tensor product combines two or more qubits to form a larger quantum system. For example, if we have two qubits, one in state ket 0 and the other in state ket 1, we can use the tensor product to combine them and create a new 2-qubit state, ket 01. This state represents a superposition of the two possible states of the first qubit and the two possible states of the second qubit. In general, the tensor product allows us to create a new quantum system that is the product of two or more smaller quantum systems. This is particularly useful in quantum computing because many quantum algorithms involve manipulating multiple qubits at once. One important thing to note is that the tensor product is not just a simple multiplication of the individual qubits. Instead, it creates a new space that contains all possible combinations of the individual qubits. This is why we say that the tensor product combines the two or more qubits to form a larger quantum system. The tensor product is associative, distributive, and satisfies the scalar multiplication property, meaning that the order in which we apply the tensor product does not matter, and we can factor out scalars from one of the quantum systems before applying the tensor product. The transpose conjugate of a tensor product is the tensor product of the transpose conjugates of the individual quantum systems. This is useful for calculating certain properties of quantum systems, such as their inner product. The transpose of a tensor product is the tensor product of the transposes of the individual quantum systems. This property is useful for certain quantum algorithms that require the manipulation of the transpose of a quantum system. The conjugate of a tensor product is the tensor product of the conjugates of the individual quantum systems. This is useful for calculating certain properties of quantum systems, such as their norm. The inverse of a tensor product is the tensor product of the inverses of the individual quantum systems. This property is useful for certain quantum algorithms that require the manipulation of the inverse of a quantum system. The trace of a tensor product is the product of the traces of the individual quantum systems. This is useful for calculating certain properties of quantum systems, such as their eigenvalues. The determinant of a tensor product is the product of the determinants of the individual quantum systems. This property is useful for certain quantum algorithms that require the manipulation of the determinant of a quantum system. Understanding these concepts is important for effectively using the tensor product in quantum computing and for developing quantum algorithms that can perform complex calculations. Here, we have presented many formulas, but upon closer examination, we can see that they are all different representations of the same operational rules. The underlying rule is that the matrix multiplication of tensor products of different subspaces is equivalent to the matrix multiplication of each subspace followed by a tensor product of the results. These formulas are commonly used in quantum circuits. Understanding the tensor product and its properties is essential for designing and implementing quantum algorithms, and for effectively manipulating quantum states. Mastering these concepts is key to making progress in quantum computing research and applications. Let me give you an example of how the tensor product can be used in a quantum circuit. Consider a composite system at time t1 in the state ket 00. After applying the tensor product of x and z gates, we can calculate the state of the composite system at time t2. After performing the calculation, we find that the composite system is in the state ket 10. This means that the first qubit is in the state ket 1 and the second qubit is in the state ket 0. The tensor product is a powerful tool for manipulating the states of multiple qubits simultaneously in quantum circuits, as demonstrated by this example. Let's take an example of a quantum circuit where we perform matrix multiplication in different subspaces and then take the tensor product of the results. At time t1, the composite system is in the state ket 00. The first subsystem undergoes an X gate, resulting in the state ket 1, and the second subsystem undergoes a Z gate, resulting in the state ket 0. We then calculate the state of the composite system at time t2 using matrix multiplication and find it to be ket 10, which is consistent with the result obtained by the overall calculation. This shows that matrix multiplication in different subspaces followed by taking the tensor product of the results is equivalent to performing the tensor product of the matrices in the different subspaces directly.